Good morning. Today we have discussed the floating point number. Floating point representation. Now question is, what is floating point? Number basically two types. Number one is the fixed point representation. Fixed point representation, and other is the floating point representation. Floating point representation. Now question is, what is fixed point representation and what is floating point representation? Suppose if we write 5.625 a number. Here before the decimal place 5 is fixed, and after the decimal place 6 to 5 is 3 position is fixed. That is the number which has fixed, this is the integer part, this is known as integer part, and this is known as fraction part. Fraction part. Both integer part and fractional part, the number of bits are fixed in fixed point. There will be no change. Okay. If we convert into binary form, then it will be 5 means 101.625 means we check it 10. So before point, so this is binary number. Okay. So these two portions are fixed in case of fixed point. If we consider this number in floating point 5.625, that is in case of floating point number. In case of fixed point number, the number of bit in the integer part and fractional part are fixed. There will be no change. But in case of floating point number, this number can change. As for example, this is the number in floating point. Now you can write from, in this way you can write, that is 5, 6, 2, 5 into 10 to the power minus 3, you can write, or you can write 0.5625 into 10 to the power 1, or you can write 56.25 into 10 to the power minus 1, 10 to the power minus 1. Okay, so you check it, this portion, this is not fixed, this is the float. That is in case of floating point number, the radix point or decimal point floats, that is not a fixed. Here the decimal point fixed. integer part, fractional part fixed, but in case of floating point, this is not fixed. So problem is here, and in representation of the floating point number is very important in our computer science. So how we will represent the floating point number? And as there is no rule, you can check infinite number of times. As for example, 5, 6, 2.5, that is 10 to the power minus 2. Or you can write 0.05, 6 to 5. You can write 10 to the power plus 2. So all are correct, infinite number. Now, for this reason, floating point is very important. So, we check it, 5.625 is the base 10, and it is converted into 101.101. It is the binary form. And I have already mentioned that we can write it 0.5625 into 10 to the power plus 1, or similarly, or we can write 5625 into 10 to the power minus 3. We can write similarly here also. We can write, as for example, if I write 0.101101, then how many points? 1, 2, 3. So 2 to the power plus 3. So you can write not 10 to the power here, as it is binary form. If I write 1.01101, then we can write 2 to the power 2. You can write, or if I write 101, then 2 to the power how many times? 2 to the power minus 3. So when your point moves from left side, then it is here, in case of decimal, 10 to the power plus, and when it moves from right side, that is in this side, then it is minus. Similarly, here is also same. That is, when moves from left side, then it is plus how many times? 1, 2, 3, 2 to the power 3. When you moves in right side, how many times? 1, 2, 3. So it is 2 to the power minus 3. So infinite number of times you can write in floating point. So we need some rule. Okay, the rule is known as normalization. Normalization. In case of normalization, you can write the floating point into a scientific manner. Okay. So we can write with help of normalization scientific notation. scientific notation. We need some scientific notation. Now, how we can write the scientific notation? So, there are two types of normalization. One is explicit normalization. Explicit normalization, and other is implicit normalization. That is, with help of these two normalization, we can represent the floating point number in scientific way. First, we discuss the explicit normalization. Now, what is explicit normalization? Explicit normalization. In explicit normalization, suppose a number is this. So this is a binary number of 6.625 5.625, and in case of explicit normalization, we will move the radix point or point where the left hand side of the most significant bit. Which is the most significant bit? 1. So you put the point is here. How? So in explicit normalization, 0.101101, and for this reason you move 1 to 3, so you write 2 to the power 3. So this is the explicit normalization. Okay. So, what is the explicit normalization? Move the bit left hand side, the radix point, move the left hand side before the most significant bit. Which is the most significant? 1. So, in left hand side. So, this is the normalization form. Explicit normalization. And implicit normalization form number 2. Implicit normalization form. Implicit normalization. What will happen? You can write this 1 point, that is, move this point here, 1.01101, and for this reason how many? 2, that is 2 to the power 2. So what is the technique? Technique is, in case of implicit, the most significant, right of the most significant, and here left of the most significant. This is the basic. So this is your actual number. In case of implicit, left of the most significant. In case of implicit, right of the most significant. Most significant is 1. So it is the form. Okay. Now another thing you have to remember, in case of floating point, there are 3 terms. There are 3 terms. This term, here is also this term and this term, that is this one, and here is this portion and this portion. This is known as mantissa. This is known as mantissa. And this 3 is known as exponent. So mantissa exponent portion. Here is also, which is mantissa? This is the mantissa, and this is the exponent. So this is mantissa. So every floating point write with help of mantissa and exponents. And also another is the sign bit. So what is the general formula of implicit? Now I write the general formula of the implicit. So this is the mantissa portion, and here is the mantissa portion. Now write the general formula of the implicit and explicit. Explicit can be represented as minus 1 to the power sign. Sign is positive or negative. In case of positive, it is 0. In case of negative, it is minus 1. 1. So this into 0 point m. M means mantissa into 2 to the power e minus bias, B-I-A-S. Yeah. And in case of implicit, what is the formula? Basic formula: minus 1 to the power s into 1 point m. This is 0 point and this is 1 point m into 2 to the power e minus bias. These are the two standard forms of implicit and explicit. Okay. Now question is, bias is the exponent, and what is bias? Bias is needed to check that here is 2 to the power minus 3, 2 to the power plus 2, to the plus, here is also minus and plus. So how we can represent this plus minus sign into a single term, that is the bias. As for example, so how we convert this portion? Actually, what happened in case of implicit? Suppose how we will convert. So this is the implicit and explicit. Now conversion. Suppose a number is convert this portion 101.101 is the base 2 in explicit normalization with 10 bits. How we convert? So this is the explicit normalization standard form: 0 point m into 2 to the power e minus bias. And I have already mentioned the bias is needed for positive and negative into a single formula. What is the formula actually here? For 10 bits. Now the number is this number. So your number is actually, this is the implicit. You write here 0.1011 0.011001. How many bits? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, and finally 1 and 2 to the power 3. So this is the explicit, but how you will represent? How you will represent? In 10 bits. So in 10 bits there are 3 portions. The first bit is the sign bit. Sign bit. So how many bits? 1 bits. Then 4 bits are the exponent bit. Exponent bit 4 bits. So total is 10. So 1 plus 4, 5, and this is the mantissa. Mantissa, how many bits? 5 bits. So these are the standard value. So you check that. I have already mentioned for the sign bit 0 for positive and 1 for negative. You will remember. So here S is equal to how much? S is equal to 0, minus 1 to the power 0, as it is positive. Then E equal to how much? And this is the main thing. E equal to 2 to the power E minus bias, that is E equal to, here the number is 3. 3 plus 8, that is 11. This is the bias. This is the bias. How you will get the bias is 11? Because 2 to the power E minus bias equal to 2 to the power 3. Then what will happen? E minus bias equal to 3. That is E equal to 3 plus bias. What is the bias value? 8. In case of 4 exponent part. So 11. 11 is binary equivalent to how much? 1, 0, 1, 1. This is the 11. So you write here. So this is the 0 bit, and 11 is right 1, 0, 1, 1, and exponent mantissa. Mantissa is 5 bits. How many bits? 1, 2, 3, 4, 5, 6. So 1 bit will 1, 0, 1, 1, 0. So 1 bit you cannot write here, as this is the maximum size is 5. So 1 bit omitted. Okay. Now, if you convert into the implicit form, the same in case of implicit form. So this is the explicit form. 1 bit is out. 1 bit is out. That is not correct answer, as the 5 bits. In case of implicit, you check it. In case of implicit, sign bit is 0, but here is, so you write implicit. What is the technique? Implicit is this. So how you can write? That is, sign is 0 and E is 2 plus 8, that is 10. 10 means 1, 0, 1, 0, 10. Now you put here 1, 0, 1, 0, and then the mantissa part. Here mantissa part is this. How many bits? 0, 1, 2, 3, 4. 4, 5. 1, 2, 3, 4, 5. So you write here 0, 1, 1, 0, 1. So you check that. In case of implicit, you complete. There is no loss. In case of explicit, there is a 1 bit loss. Okay. And another thing, as I write the bias, one thing, another example, for 10 bits, I write another example, 0.01, 0.0101, 0.0101 base 2, and convert into, so this number is explicit. You can write explicit, that is this number 0.0101 in explicit normalization. Now first you write here explicit, that is, this is the most significant bit, so 0.101, okay, 101, and for this reason you need 2 to the power minus 1 for conversion. So here S is equal to 0 and E equal to minus 1, 2 to the power minus 1 plus 8, that is 7. 7 is equivalent to 111, you know this. And so if you represent in 10 bits, so first bit is the 0, this is the side bit, and then the 4 bit is the exponent is 111, but it is need for 4 bits. And what is the mantissa? Mantissa is 101, but you need how many bits? 5, so you can write 20. Okay, so in this way you can write or convert the floating point representation. Okay, so you have to remember, one is the sign bit, and that is the exponent, and third is the mantissa. Mantissa in case of this 101, but you need the 5 bits. Okay, so today up to this the floating point, and in your next semester there are so many things about the floating point number. IEEE 754 representation we will discuss in your next semester. Okay, up to this complete.